Okay, I guess we can start. All right, Wednesday, right? How are you?
Good.
Okay. Okay, so we are in a different energy balance, and Monday you learned long wave radiation and emissivity and all. So I got a few questions. In a long wave radiation, why we don't feel that, right? Even though the surface is emitting so much, because we are emitting back the same amount. Why we feel the sunlight, solar radiation, because we are not emitting solar radiation from our body. So that's why we are receiving mostly regarding solar radiation. Therefore, you feel a lot of radiation hitting your body. But in here, you are emitting and then receiving. It's about the same or close to the same value. You probably higher temperature, so your long wave radiation is probably greater than whatever you are receiving. Okay? All right. It's once you understand this is very simple, but first time it's probably counterintuitive because you don't see it. Okay. And metal and plastic, particularly polyethylene material, has a very low emissivity. And metal, because it deflects long wave radiation, and then if it's aluminum or metal surface, it deflects. So that means absorbance of that surface regarding long wave is very small, and absorbance equal to emissivity, so that means emissivity is small. Emissivity is relative to the black body radiation, right? How much actually emit compared to the black body at the same surface temperature. Perfect black body, I should say. Emissivity equal 1.0, right? Yeah, the plastic material, polyethylene, the emissivity is low, something like a 0.15 in my reference table. That's because it transmits long wave radiation. So it's not opaque to long wave radiation versus glass is very opaque or relatively opaque. So that means absorb a lot of long wave radiation versus polyethylene film transmit and doesn't absorb long wave. And then we come back to the point doing some exercise, and then you probably understand better that way. Okay, any other burning questions regarding long wave thermal radiation?
So
Jessica.
If it reflects light like metal, it'll have a lower emissivity.
That's right. That's right. Yeah. So that's why when you're standing in front of the metal surface, cold metal surface, you feel cold because it doesn't emit long wave radiation, even though the temperature may be the same as like painted surface, because it doesn't emit. So you are losing more relative to what you receive. Any other question? All right. Okay. So, so I'm finishing up the leaf and canopy temperature, energy balance lecture today. All right, so the same reading material. So the keyword, we went long wave radiation and short wave radiation. The reason I call long wave is because, clearly the range of wavelengths, for short wave, which is solar radiation, and long wave are completely different because of the surface temperature. So that's why long wave and short wave. That's the exercise we did, 400 some watt coming from the temperature 24 degrees C. And this is also graph showing under a direct solar radiation 840 watt per square meter, so that's relatively high, right, close to the summer radiation, which is 1,000. It's a lot of solar radiation. And compared to the infrared radiation emitted by the leaf surface, having the temperature of 25 degrees C. So the distribution, note that this is a log plot again, so that's a log scale, so that's why it's not evenly distributed, because it's such a huge, range. It's just difficult to show in one graph. So, but anyway, the amount of radiation is equivalent to the solar radiation. Okay, the amount of radiation emitted from the surface of the leaf as a long wave is about the same as what is receiving. But at the same time, which is not shown in here, leaves are receiving long wave radiations from the surrounding objects, right? Any objects having temperature greater than 0 Kelvin emit long wave, right? So the greenhouse structures, neighboring plants, or whatever emitting. So what is actually contributing to warm up the temperature of the leaf is the net radiation, net long wave radiation, and net short wave radiation. Okay, right. A little bit more example to hoping that it would help you to understand. So cold night, we don't have many here. Even though the air temperature in the room is maintained by heating system, when you stand in front of the cold window, glass window, you feel really cold, even though the temperature is fine. And then to prevent that, you put some thermal screen or curtain, and then having one layer between yourself and cold surface, that helps a lot to warm you up. The reason, because surface temperature is obviously different. All right, so the one before is, let's say outside is -1 degree C, right? It's freezing cold. So the window surface is relatively close to that temperature, right? The window surface. So when you are sitting or standing in front of the window, even though air temperature is heated to the 15 or 20 or cozy room temperature, the surface is -1 or close to that temperature, outside temperature. Therefore, it is emitting very small amount of long wave compared to what your body is emitting, right? So that you are losing a lot of long wave radiation between you and basically toward the window, right? So that's why you feel cold when you are standing in front of that cold surface. TJ?
You say that the long wave radiation goes from or travels from bodies of high radiation to low radiation?
As a net, yes.
Okay.
Yeah, so everything is emitting, but what you receive is the net, right, balance. If you are receiving more, you save or you gain more. If you are receiving less energy, less radiation, you're losing more. So it's a net of those incoming and outgoing radiation. Okay, so when you have this, curtain, right? So that curtain create a little bit higher temperature than -1 because it's getting closer to the air because curtain is sitting in the air, right? So maybe not 15 or 20, but maybe 8 degrees C or 10 degrees C. So now temperature increase, so that increasing long wave radiation coming from the surface of the curtain, therefore you don't lose that much of radiation energy, right? Because of that, right? The same thing is happening in the greenhouse. Okay, nighttime it's very cold, and then PE, polyethylene film, is very transparent relative to the long wave. So the plants lose long wave radiation to the outside because the surface almost doesn't exist relative to the long wave radiation. So when you have a one layer of thermal curtain, it's just having one layer in the greenhouse, that would help, keeping temperature, body temperature, warmer, much warmer than it was before. Okay, we had that issue in a greenhouse, Polytech greenhouse. That's the round shape roof greenhouse. We didn't realize that. We didn't think about because it's a polyethylene greenhouse, and then our tomato didn't ripe. It's a very slow ripening, and then we realized that maybe the surface temperature is very low, so we put the thermal curtain, and then that helped a lot, accelerating ripening speed because the surface temperature is very different. Another example, when you go to restaurant in wintertime, there is a radiative heater outside, right? And that is not heating the air. It may be heating a little bit, but effectively heat your body, right? So that's why they use that. So that you are sitting, under the radiative heater, you feel really warm, cozy, because you're receiving a lot of long-wave radiation from that surface. Okay? All right. So this one is lot of information here, but it is showing a radiation balance at night in terms of long-wave radiation. So again, from any surface having temperature greater than 0 Kelvin, emit long-wave radiation. And then let's say this is a ground surface, soil or whatever ground. And then the temperature T, okay, and then the amount of long-wave radiation you can compute using a Stefan-Boltzmann equation. So the long-wave radiation upward, from the surface to upward to the sky, is given by this equation, epsilon, right? Epsilon, which is the emissivity, sigma, which is a Stefan-Boltzmann constant, and then the temperature plus 273 to make it Kelvin, to the power of fourth. And that gives the energy emitted from the surface. Okay, sky has long-wave radiation too, downward. And then that is, you can estimate that amount based on the air temperature, ambient air temperature. It's an empirical way to estimate. And usually this is a compensation, the correlation factor, temperature correlation. And that's depending on the conditions, cloudy or the overcasting. But when it is clear sky, under certain conditions, you can use 20. So you don't need to remember this. It's just to understand how it works. So clear sky, you can use 20 Kelvin as a correction factor. So that means, let's say your air temperature is 10 degrees C, and then minus 20. So that means almost the same as the surface of minus 10 degrees C, in the sky, right? So that is what correlation does. And then you don't need emissivity for the sky, because you can correct the value using correlation factor. But anyway, so this gives, based on temperature in the air, but this gives a very small amount of long-wave radiation, downward. So a lot of long-wave radiation coming upward, from the soil or ground, and then very small amount coming downward. So the difference is the difference is actually different terminology. Effective radiation, so that's directly affecting losing temperature or gaining heat of that surface. Effective radiation. So long-wave radiation, effective radiation, is upward long-wave radiation from the surface, and downward long-wave radiation absorbed, because not all the long-wave radiation is absorbed by that surface, and you need to use emissivity, because emissivity equals to absorptance. So emissivity times downward long-wave radiation from the sky is the absorbed long-wave radiation. So the equation is now the effective radiation equal long wave radiation from the surface minus emissivity times long wave radiation from the sky. So that gives you the value in terms of long wave radiation. And then this can be applied directly to the leaf surface, right? So the leaf surface, the same thing. It's just long wave radiation from the sky can be estimated by the ambient temperature, and then leaf temperature can be used to estimate amount of long wave radiation coming from the surface, and then exactly the same equation. Effective radiation that the leaf surface lose or gain equal upward long wave radiation from the surface of the leaf determined by the leaf temperature minus emissivity of the leaf times long wave radiation from the sky, downward one. Okay? Okay, so this is a very simple example when leaf is sitting in an open space. If it is surrounded by other objects, neighboring plants, inside the canopy, then of course this term, whatever hitting that particular leaf, is going to be the summation of all the long wave radiations coming from all the different objects, including sky, right? Okay? All right. So now including short wave radiation to the equation, all right, we understood now long wave radiation balance. So the short wave radiation comes during the daytime, right? During the nighttime, we don't have that. Okay, so the previous two slides are basically during the nighttime. This is during the daytime, the short wave radiation coming in, and not all of them is absorbed. Some of them reflected, some of them transmitted. If it is ground surface, it is a good assumption that there's no transmitting, short wave radiation, right? It's a ground, so it's eventually absorbed. But there is reflection. So that's why this equation have just reflectance included. So the 1 minus reflectance equals to absorptance, in this case, for the short wave radiation. So that this is the same long wave radiation or effective radiation of the long wave. And then this is a term for short wave radiation. And then the sum of those is the net radiation. So the net radiation means that it's the total of incoming long and short wave radiations and outgoing long and short wave radiation. Okay? And that is the component contributing temperature increase of the plants or any surface. Yes?
What was net again?
Net radiation.
Yeah.
Here it is, net radiation. Net radiation that ground surface receives. So that's, see the equation? So that it has a long wave radiation component, upward and downward, and short wave radiation incoming minus reflected. Okay? All right, so that's the big component contributing to the energy balance of the leaf. And then of course, over the leaf surface, the same equation can apply, right? This one assuming we don't have, or we can ignore the transmittance, okay? All right, so let's do a little practice. Oh, okay, hold on, give me a second. I printed 2 pages to do that. Okay, so this is a little house, and then it's a cold, clear night. Elmo. and move. Okay. Okay, so the temperature, so it's a cold, clear night, winter time. All right, a little bit. Okay, so let's see, our temperature is 0 degrees C, okay? And then that's very dangerous, right? If you're a horticulturist, you have to pay attention to your plant. It might have chilling damage or freezing damage, right? Because the surface temperature could be lower than the air temperature. And why? Do you know the surface temperature could be lower than the air temperature? Clear night, clear sky, night, because the surface loses thermal energy by long wave radiation. Okay, so it's emitting toward the sky. Okay, so that's why the surface goes maybe -5 degrees C. All right, because a lot less is coming from the sky, right? Because the sky temperature is, if the air temperature is 0 degrees C, sky temperature is basically -20 C in my empirical relationship. This could be very different, but let's assume this is correct. So the sky temperature is -20 degrees C. From that surface, the long wave radiation is tiny, right? Because we are talking about force power. So the leaf temperature is -5, or even 0. It's compared to the -20. The amount of radiation emitted from the plant is a lot. So that means reducing, the temperature, lowering temperature. Okay, so that's why it's potentially frosting or damage, freezing damage or chilling damage occurred on the leaf. Okay, now the house temperature is also about the same, right? -5 or so, because it's losing the same. And then emissivity is about the same, 0.95, 0.97. It's just basically the materials having that high emissivity. Okay, so if you look closely to this plant or tree, which side of the trees is likely to get more damage by chilling? Right-hand side, open to the sky, or left-hand side, close to the house? Right-hand side. And why is that? Yeah, exactly. So the house, we assumed about -5 degrees C. So that is emitting toward the plant too, right? So the plant is emitting, but it's about the same amount is coming back from, can you see? Okay, from the house. So the house side is protected basically, but open side is unprotected or non-protected, therefore losing a lot more energy. So maybe eventually, right, by the time temperature reached the lowest point of that night, this surface could be -10, right? Because it's continuously losing, so that would reduce the temperature. And that's why you always have damage this side, but not the other side. Same thing, when you park your car, right? And house side is protected, but the other side, the rear wind or rear wind, get frosted, right? So the difference, you see that. And exactly the same reason. It's open to the sky, therefore the surface temperature is lower, right? So how do you save this plant? Build another house. I like you. Yeah, it's an expensive version, but it works. Okay, so Ken is gonna build another house in here. Okay, so what else? Cover it. What kind of material you use? Insulator. like a styrofoam. Yeah, that works too, but you don't have to use actually styrofoam. Bed sheet. Why? Have you ever thought, like why just thin layer of bed sheet can protect the plant from freezing? For example, freezing, temperature outside, right? Can you survive just one layer of bed sheet? No, right? Why plants can survive or protect, at least not to give the freezing damage? Okay. I can't hear you.
The radiation?
Yeah. Think you're talking about radiation, right? So it's one layer of bed sheet right here. Okay. Right. What's the surface temperature of the bed sheet now? -5. Yeah. Okay. -5. Yeah. I take that. So a lot warmer than sky temperature, right? That's why it reduced the long wave radiation. The loss of long wave radiation. So more long wave radiation coming from that -5 degrees C surface compared to -20 sky. That's why plants don't lose that much of long wave radiation. Okay? So why it has to be cotton bed or whatever the bed sheet? Why not big jumbo grocery store bag or garbage bag, plastic?
Those would have low emissivity.
Yeah. The plastic bag, typically low emissivity and high transmittance of long wave. So that everything plants emit goes away to the sky, and then the surface, even it is -5 or minus, or close to 0, because of the low emissivity, it doesn't contribute to keep the plant temperature higher. Because plants lose the long wave anyway with that plastic material covered. Right? All right, so that's the reason. Okay, one more exercise. So here is 2 greenhouses. One is polyethylene film. Maybe this is a high tonal. Maybe this is a just a glazing with plastic, just like the other greenhouses. And then the next to it is glass. So the glass emissivity is 0.9 or so. Maybe 8. What was the value I got as a reference? Or 0.88. But that's okay, 0.9. Right? And then PE is 0.15. Okay? So those 2 greenhouses. Which of the 2 plants is likely at higher temperature at night, clear night, cold? Glass, yeah. The same reason, the bed sheet versus plastic cover.
Can you repeat your question?
Oh, question? Yeah, so let's see, this is a plant temperature, and this is a plant temperature, 1 and 2. Which one is likely to be higher? So the glass is higher because it doesn't lose under the polyethylene film, because it has a very low emissivity and then also transmit a lot of long wave. This plant lose a lot of energy, heat, by long wave at night. Surface temperature is much lower in the sky. Glass, because it doesn't transmit as much, and then the emissivity is high, so it's re-emitting to other plants. So that plant doesn't lose much radiation energy under the glass. Yes?
Do we have the emissivity value for water?
Yeah, 0.9 or so.
Is it high, like
High, yeah. Oh, yeah. Water is high. So if you have a water surface condensation, that protect perfectly.
Really?
Yeah. So some people use actually water over the plastic materials to protect the long wave radiation.
Inside is condensation.
Naturally it reduces, yes. Yeah, if it is entire surface, yes.
So the PE has a higher absorbance?
No, very low absorbance.
Oh, I mean, higher, is it higher than glass?
Absorbance is low. The absorbance is same as emissivity
Right.
in terms of long wave radiation. So the from the plant surface, long wave radiation is emitted and then doesn't get absorbed by the film surface, transmit, so that goes through, go out. Here, it hits and then absorbed, nearly 90% absorbed, right? And then we emit that toward the plants. So you're saving an energy basically by selecting glass over the polyethylene. Someone tried to. Yeah, so it's quite interesting, huh? And then just by looking, you can't tell. Both are looking exactly same, exactly translucent, clear material, right? But in terms of long wave, because it's a range of radiation you can't see, you really cannot see the properties until you actually measure it, the property. And there is a method to do that. We don't have that in this center. I wish we have, we had, but we don't have that.
Can we use this information to calculate the amount of energy lost between the two types of material? And figure out.
Yeah. Which one is energy efficient? Yes. Oh, yeah, we can do that. We can do that. So if you are taking Dr. Giacomelli's course, I bet he is introducing U value, which is sort of how do I say? It's a total value considering all the radiative loss and then also convection, conduction. It's a simplified coefficient to estimate energy loss from the greenhouse. But what I'm teaching is a more detail. So the YU is high for whatever materials, YU is lower for whatever material, because U value is based on the materials you are using for the greenhouse. Okay? All right. Yeah, so the water is 0.92. So it's the same, almost the same as glass. All right? Okay. Any question? It's quite interesting, right? So the everyday life is connected. That's why this is also usually you learn in meteorology, meteorology. That's how you pronounce it. Meteorology lecture, because it's very important concept to understand the temperature. Okay, so net radiation, basically including shortwave radiation, long-wave radiation, and then two more components you need to learn today: sensible heat transfer and latent heat transfer over the leaf surface. And then, as a result, there is a change in leaf temperature. Okay, if incoming energy is greater than outgoing energy, then temperature needs to be increased. That's energy balance, because energy is conserved. And there's one more component in the energy balance of the leaf, metabolic heat, which is very small. So we usually ignore when we think about energy balance. So the balance equation is net radiation, sensible heat, latent heat, metabolic heat, or the change, internal change that is contributing to the temperature change, increase or decrease. So that's the energy used to increase the mass of fresh weight leaf. So that's the equation. So what is sensible heat and latent heat? Okay, sensible heat is basically the heat transfer relative to the temperature difference. So when you have two objects, right next to each other, and then having temperature difference, high temperature and low temperature, and sensible heat always, transferred from high temperature side to low temperature side. Heat transfer from high temperature side to low temperature side. That's not difficult, right? The low temperature side gain heat from high temperature side. That's sensible heat. And this is an equation, temperature difference, so that's a driving force. And then heat transfer coefficient, and this is depending on the kind of materials. Is that fluid or is that solid to solid transfer? That is depending on the conditions, but based on the temperature difference. And there is a temperature difference, then there is a sensible heat transfer from material A to material B. In leaf case, or leaf balance case, leaf to the air or air to the leaf. If leaf is sitting very cold temperature, leaf loses some heat by sensible heat. Right? If it is opposite, if air temperature is warmer than leaf temperature, then that's the time leaf gains some heat from the air, right? Due to this sensible heat transfer. So the direction of heat transfer in terms of sensible heat is based on which temperature is greater. Caitlin.
So if you have, for the heat transfer coefficient, let's say you have the two different materials, like plastic and a metal together, and they're the two solids, which of those coefficients would you use? Would it be the one that's colder since the energy is moving to that one?
I think the way you do, if I'm understanding correct, you have to take the traveling path, how much, in material A and material B, and then average out. I think that's the process. I may be wrong for that question, but that's probably, so you take, for example, some materials a sandwich of 2 or 3 materials, or the combination of, like a panel, plastic and wood and plastic. And then in that case, you can actually compute the average heat transfer coefficient using the width or depth of each material, and then difference value of each material. I may be wrong, but that's what I recall how you do. And then that kind of question probably you can learn in the engineering course. Okay. Any other question regarding that sensible heat? So sensible heat is very important component, all right? Every time you have a temperature difference, this happens. High temperature to low temperature. Latent heat is super important, okay? Sensible heat is important, latent heat is super important for plants, because that's the heat transfer associating with phase change, meaning from liquid to vapor, vapor to liquid, which is condensation. Liquid to vapor is evaporation, transpiration, right? So when water evaporates, a lot of energy, a lot of heat is basically taken up. So that's why it cools the surrounding air, surrounding object, the water is attaching to. So if water is evaporating from the surface of leaf, most likely it is sucking heat from the leaf, because to change the phase, it needs a lot of energy, and that's latent heat. Opposite case, when vapor condense on the leaf and make a dew, right? Condensation, it generates heat, so warms up the surface rather than cool. Okay, so that's latent heat. And then if you know the mass of water evaporated, you can estimate how much energy was taken up. And that's here at 20 degrees C, 2.454 megajoule per kilogram evaporation. So this is a latent heat for evaporating water. Okay, so take that information, right? Take that information. To start with simple example, so we have, let's see, we have net radiation, 700 watt per square meter coming to this single leaf. Okay, that includes shortwave radiation and long-wave radiation. I'm not specifying, how much shortwave radiation contributing, but let's assume net radiation after taking into consideration the whatever reflected or whatever emitted from the leaf. But net radiation, net is 700 watt per square meter. So assuming transpiration rate is going from that leaf per square meter base, it's 200 milligram of water evaporating from the leaf per second. And then from that information, you can actually estimate how much latent heat transfer, in this case loss, right? Cooling. How much latent heat transfer is going on. That is cooling, so therefore negative 486 watt per square meter. Using that 2.43 megajoule per evaporating 1 kilos. So that is basically gives this number, 486 watt per square meter. Okay, so that's a loss by latent heat. Incoming is 700, and outgoing is 486, right? So it's not balanced yet. So what happens? So the temperature in the leaf, temperature of the leaf needs to increase. Okay, because you get more energy than loss, then you got to have temperature increase, internal change, right? So once you have the temperature increase, oh, that's a not good example.
So in that slide, the leaf is warming up or
Warming up, yeah, yeah. If not, if temperature is not changing, so that's what we call steady state condition. That's the actually example I had. So let's assume temperature is not changing. So in that case, sensible heat transfer must be happening. Okay, so the latent heat, 486 watt per square meter loss, incoming 700. So it has to be balanced, therefore 214 needs to go out by sensible heat to balance out everything. Okay, so that means going out means temperature in the leaf must be higher than air. Otherwise, sensible heat doesn't go that direction. Sensible heat needs to go, right? So understanding energy balance is very important tool for understanding, the relationship between leaf and air temperatures. Okay, because of the equation, net radiation plus sensible heat, positive value when temperature of the leaf is greater than air temperature, negative value when temperature in the air is greater than, the other way, sorry. Negative value when plants are losing heat, so that means temperature of the leaf is greater than air. Then sensible heat is negative, losing heat. The other one, when temperature in the air is greater than leaf, then plants are gaining the heat. In that case, positive value. Latent heat, transpiration going on, then the negative value. So losing heat or cooling by transpiration, latent heat exchange. And then this can be ignored because it's very small, including energy used for photosynthesis. Remember, photosynthesis, very, very small amount of radiation used. Therefore, it's usually ignored for energy balance. Okay, for photosynthesis and assimilation, you can't ignore, but if you're talking about energy balance, much, much bigger energy coming in and going out, therefore photosynthesis is negligible. Respiration too. And whenever it's not balancing out, then what happens is internal change. So if you sum up everything, the balance equals to 0. That's why we call this is an energy balance equation, equals to 0. Right. So that's how we use incoming 700. We know latent heat minus 486. If there's no leaf temperature change, then sensible heat got to be 214. If sensible heat, if you can actually compute sensible heat, for example, then if it is not balancing, summation is not 0, then you have to see some kind of temperature increase or decrease, right? Internal change. All right. So for example, right now it's balancing, it was balancing, oops, right? And then you cut the petiole, right? And then cut basically the vascular water flux. And then in that case, latent heat declines. Latent heat declines. Why? Because transpiration is no longer, right? So just residual water is evaporating. So it's not active transpiration going on. Maybe stomata close, sensing that water stress, and plants close the stomata, right? So there's no latent heat transfer or reduced latent heat transfer significantly. And then in that case, still the leaf is receiving, the same amount of net radiation, 700 watt per square meter, right? So in that situation, leaf temperature got to increase. Leaf temperature, because the same incoming but less going out by transpiration, so leaf temperature increase. And increased leaf temperature actually drives more sensible heat transfer. Okay, so that's why big red arrow you can see in here, right? Because of the temperature increase the temperature difference between leaf and air, and then increase sensible heat. So temperature increase and sort of level off whenever the sensible heat reach or compensate the loss of latent heat. Are you with me?
Me?
Yeah?
Oh,
Okay, good. Good. All right. Now, so that's why you have seen this. The sunny condition, more net radiation, cloudy condition, reduced net radiation, but maybe still doing transpiration. That's why the leaf temperature could be lower than air temperature, because losing a lot more by transpiration than received by net radiation, right? So it could be lower than air temperature. And now, the weather comes back to sunny, and then just same thing. Okay, so it's super, super understandable once you understand the energy balance over the leaf. Okay, all right, you learn the boundary layer, right, in the wind effect on the plants. So the boundary layer exists and affects the latent heat transpiration, gas exchange, right, boundary layer. Wind reduce the boundary layer, reduce the resistance, so increase the latent heat transfer, transpiration. Reduced resistance, increase the transpiration rate. Okay, same thing over the sensible heat transfer. Okay, heat transfer is affected by boundary layer too. And then that is pretty much affected. So the high wind, sensible heat, and latent heat transfer, both of them are, under high wind, both of them are enhanced, increased, right? All right. And then latent heat transfer, of course, since it's transpiration, there is stomatal resistance. Okay, stomatal resistance is regulating that latent heat transfer. Okay, all right. This one, I think this is coming from the Yeah, the reading material of today, actually from Monday, the same thing, same chapter from plant ecophysiology. This is showing energy balance of the leaf attached to the ground or sort of in the air, and then showing the difference. And then the one attaching to the ground showing 51 degree C, and which is hanging above or lifted above is 36 degrees C, much lower temperature, even though soil temperature is the same. And that difference you can now describe based on the energy balance of the leaf. So there is a long wave radiation, short wave radiation, and then long wave radiation from the soil. And then in here, convection is basically sensible heat transfer, convection conduction, sensible heat transfer. And then that is happening both sides. Therefore, when leaf is lifted up, convection is greater compared to the attached situation, which is 180. So understanding that, you can describe something like this, ecophysiological or ecological temperature distribution in an ecosystem as well. So now we are expanding this understanding from leaf to the canopy, right? Because many plants in the horticulture application, agriculture application are in the community, plant community canopy. Right, so you can expand that leaf energy balance to the canopy level easily. It's just that instead of many leaves, you can think about this is a big gigantic leaf sitting in a growing area. So you can take the net radiation over the canopy as an incident net radiation. Again, it's a short wave radiation, long wave radiation. Both are taken into consideration, right? Not just downward, but deflection, and then also emission from the plants. If it is sitting inside a greenhouse, the surface of the glazing also emit long wave radiation, so that's also taken into consideration to compute net radiation. There's a sensor, by the way, to measure net radiation. Usually having, the good one is having two sensors. One is for short wave radiation, the other one is for long wave radiation, and then you can measure the downward and upward, coming from the bottom or coming from the above at the same time. So that's a net radiation sensor. And then sensible heat transfer is going. If you consider this as a big leaf, the same thing. Temperature difference is driving force of the sensible heat transfer. And then wind effect, right? Because boundary layer is affected, and boundary layer affect the sensible heat transfer. Latent heat as a whole canopy, canopy transpiration, so that latent heat exchange is going on over the plant canopy too. And then maybe one more component if you want to add when you are talking about canopy energy balance, that is a heat transfer between the canopy and soil, because the plants are attached to the ground, therefore there is a heat transfer between those two. So as I said, boundary layer for both heat transfers, and then latent heat, you have a sort of representative stomatal conductance over the canopy. Okay. Here is the equation. It's just the same thing, but bigger scale. Net radiation, incoming radiation, sensible heat transfer, latent heat transfer, change in plant canopy temperature, and then metabolic heat and ground heat transfer or soil heat transfer. So those are the components. So basically what it says is the same understanding of single leaf can apply to the canopy level, right? Okay, so here is a data. One of the graduate students in my old lab did this analysis. So this is very small canopy, This is a seedling, young seedlings. I think it's a tomato seedling. Tomato or eggplant, I forgot which one was that. But high density canopy. The size of the tray is 30 centimeter by 60 centimeter. He had 2 of them. And then he had a whole bunch of sensors, thermocouples, fine thermocouples to measure the leaf temperature. And then also the whole thing was sitting on the electric balance to measure the water loss from the entire canopy so that he can measure the transpiration rate. So what is showing here is from the bottom one, this is the leaf air temperature difference. The chart, the lowest chart is the leaf air temperature difference. So the leaf temperature minus air temperature, okay? So the positive value meaning leaf temperature is greater than air temperature, okay? So the initially 1 degree C higher in the leaf compared to the air, and then it was like that, or it's a little bit less, but certain point after 12 hours of this measurement, it start increasing, right? And then 5 degrees or 6 degrees greater temperature than air temperature. And this condition was very constant, temperature and humidity. Radiation was also constant. It was actually a growth room, so the artificial environment, electric, lighting, so it's very constant environment. So something is triggering this temperature increase, right? So what is that? Let me explain the other 2 graphs in here, two charts. So the second one is the evapotranspiration rate. He could call that transpiration rate, but he can't, confirm evaporation was negligible. Remember the transpiration is evaporation from the plant tissue. And he had soil, the substrate, wet substrate, so there is some there is some evaporation in addition to transpiration, so that's why he wanted to call that evapotranspiration. Okay, but I would assume 90% or so is transpiration, because plants are very dense canopy. But we couldn't, estimate how much is coming from transpiration or evapotranspiration. But anyway, so we call that evapotranspiration. And then it's based on the weight measurement on the electric, balance. So you see that constant evapotranspiration up to 12 hours and then decline, right? The top graph chart is showing latent heat and sensible heat. And latent heat is computed by evapotranspiration rate, because we know how much energy is taken up by evaporating 1 kilos of water. So as long as you know evapotranspiration rate, you can compute how much latent heat exchange is going on in this plant community or canopy system over the trays. So this is a computed latent heat. So it's basically following the pattern of evapotranspiration rate, right? So when it is stable, it's relatively stable. When it started declining, it started declining, okay, latent heat. And then sensible heat was estimated as a residual of the equation, energy balance equation. But it is clearly showing that sensible heat is stable up to 12 hours and then increasing, okay. So here is another information. The irrigation happened at the time 0 and 16 hours. Okay, irrigation happened. So how do you describe this particular change happening between 12 hours and 16 hours? The increase of leaf temperature, how do you describe that? Why temperature increase during that time period? And what is the evidence of that?
Because the evapotranspiration rate is decreasing.
Yeah.
Lost.
Yeah, because evapotranspiration rate is decreasing, therefore less heat loss by sensible heat or latent heat? Latent heat, yeah. So why evapotranspiration decline?
Maybe just because just like needed more water.
Yeah, plants are growing in a tray. So substrate probably started drying up. So that giving a water stress. So that's why plants closed stomata. That's why started reducing transpiration. So the reduction of the transpiration is the first event. Okay? And then because of that, the first event is the reduction of transpiration. Because of that, leaf temperature started increasing, right? Because the net radiation is the same. Okay? Evapotranspiration declined, therefore latent heat declined. And because of that, leaf temperature started increasing. And because of that, sensible heat increased. Because leaf temperature, air temperature difference is greater. All right? And then after watering, it's not clear trend, but it shows leaf temperature comes back, right? I don't know what happened in here, but it's kind of showing, right? So the water comes back, the substrate water content comes back to the optimum level, and then plants started evaporating, transpiring again. So the latent heat comes back, and sensible heat, it sort of comes back, but it's not really the same level. Something else was causing this. But, so this is a sort of exercise I wanted to do with you. Now you understand energy balance, so you can clearly explain what is happening in the energy balance. Okay? All right. Any questions? Good. All right. So what I want to do, since I have a little bit more time, I want to take you guys to the veggie box today so that we're going to see our veggie box. Okay?